John, and everyone else who helped put those together. Well, I guess I was along also, and Francis Clark and Susan Marsh as well. On to our speaker. Dr. Bob I.Tilling was born in Shanghai, China. Bob arrived in the United States, grew up in Southern California, got his bachelor's from Pomona and his PhD from Yale. He joined the USGS, mostly working on volcanic eruptions and associated hazards in the United States and elsewhere, beginning with his assignment to the ever tough Hawaiian Volcano Observatory, which that must be a great assignment. During his career, he has authored or co-authored over 350 geoscience papers and abstracts. In between research assignments, Bob held a number of managerial positions with USGS and worked as a consultant to numerous foreign countries, too many to name actually, regarding volcano hazard programs. In 1980, while serving as chief of the USGS Volcano Hazards Program, guess what happened? Mount St. Helens. And Bob coordinated the scientific response to the catastrophic eruption of Mount St. Helens. Although officially retired for almost 20 years now, 19, Bob continues volcano hazard studies as a scientist emeritus with the USGS Volcano Center in Menlo Park. Throughout his career and retirement, in addition to all the 350 plus papers, he has produced a number of general interest publications, which would be appropriate for all of us, including the best-selling map ever produced by the USGS, The Dynamic Planet, the world map of volcanoes, earthquakes, impact craters, and plate tectonics. Bob co-authored the accompanying booklet, This Dynamic Earth, again, basically all about plate tectonics. Bob and his wife Susan spend part of every summer here in Jackson with their younger daughter and family. They enjoy foreign travel, good wine, and as a board member of GJH for the last 6 years now, Bob has given lectures basically every single year, organized 2 field trips for 40 plus people to Hawaii, and continues to serve on the website committee. So Bob, thank you for all that you do, and please join me in welcoming Dr. Bob I.Tilling.
Thank you. Thank you. Thank you. Well, can people hear me all right?
Yeah.
Anyways, it's always a great pleasure to come to Jackson. And it's always a great pleasure to talk about my favorite topic, volcanoes. And this evening, Hawaiian volcanoes, the Kilauea and Mauna volcano. I think in 3-4 years ago, I gave a talk on the 2018 eruption of Kilauea. And this is just kind of a follow-up sequel to that talk. So without further ado, I will start, but I'm sorry that you cannot see the full-blown screen. That this should be the full screen, but it isn't. Okay, here we go. Well, what I'd like to do is actually just briefly introduce Hawaiian volcanism, the hotspot theory and all that, but most of you already know that, so I'll go through that fairly quickly. And then a brief recap of the 2008 to 2018 Kilauea eruptions. Pardon me for my voice, it's kind of hoarse. And then I'm going to talk about the lava lake activity since 2018 at Kilauea. And then at the same time, while I was going on, Mauna Loa erupted in 2022. So I'll show some scenes of that. And then finally, what's going on in Hawaii now. As all of you probably know, the Hawaiian Islands are part of a huge volcanic mountain range that starts from the Hawaiian Islands and goes up to the Aleutian Trent. It's more than 6,000 kilometers long, and it's the focus, the volcanism inside the Pacific plate, keeping in mind that nearly all volcanic eruptions tend to occur along the boundaries between the plates. But Hawaii is one of the really well-known exceptions where the volcanoes are inside a plate, in many cases, thousands of miles from the nearest plate boundary. Now, the island of Hawaii itself is composed of 5 volcanoes, as shown in the slide here. And all the eruptions at these volcanoes either take place at their summit, craters or calderas, or along rift zones. And I think you all know that. And the areas that we are going to talk about this evening will be the lower East Rift Zone that erupted in 2018. And also the summit of Kilauea at the caldera. And this map just shows a little bit more in detail. I'd like to point out that the Pu'u'o'o eruption is one of the longest lasting rift eruptions in recorded history. There might have been longer ones in prehistoric times, but this is the longest historic duration. Here's kind of a cartoon just showing how the whole system works. We have a thermal input, the thermal plume, the Hawaiian hotspot that brings up heat and also molten rock to a reservoir system beneath the volcano. And then from there, magma ascends to erupt onto the surface, either at the summit or after lateral migration to erupt along a rift zone. Now, in April of 2018, the Pu'u'o'o eruption, the East Rift Zone eruption at that time, started to collapse dramatically. And this picture shows that. And a huge plume of mostly debris and some magma, but mostly solid materials, rose up. And it started to collapse dramatically. And here's a view before the collapse on April 30th. And the next slide shows that huge hole after that collapse, draining out all of the active magma inside. And that sudden movement, the draining and then the migration of magma down the rift zone from the summit increased the seismicity dramatically. And it started heading east down the East Rift Zone. And finally, on May 3rd, the first eruption in that area broke out in Leilani Estates, called Fissure 1. And then subsequently, many more fissures opened up, as shown in this slide. In fact, up to 24 of them. But the main one that really produced the lavas that affected the area was Fissure 8. Okay, I'm going to try to show a video here. I hope it works. This is some drone footage of the activity feeding a massive flow on the 29th of June. As you can see, there's copious amounts of magma being erupted and flowing down the flanks. No, that's real time. That's drone photography, and near the vents, the magma moves very quickly because it's fluid. I think this will go for another minute or so. I want you to appreciate it, but this is kind of the typical activity that was going on in 2018. A very typical Hawaiian style eruption. Okay, we'll go to the next slide here. And this flow then, fed by Fissure 18, flowed more than 10 miles, ultimately putting lava into the ocean to form new land. This slide here shows the area in pink, the lava that was put out during that eruption in 2018. And you can see from that slide there, a lot of new land was created beyond the shoreline. So the big island of Hawaii now is even bigger than it was before. Now, this eruption had great impact, and it was highly significant. It ended a 35-year-old long eruption Pu'u'o'o on the rift zone. And it was also the largest lower east rift zone eruption and summit collapse in at least 200 years. So in terms of historical activity of Kilauea, this was really a big deal. Lots of land got covered up, and 900 acres of new land was created by lava flows entering the ocean. But also in the process, a lot of people were affected. 2,000 people had to be evacuated from the subdivisions, and 700 houses were destroyed, burned up by the lava flows. And then 30 miles of roads were covered by the fresh lava. And this is just showing one of the houses being consumed by the lava flows. Now, while all that lower East Rift Zone eruption was going on, the summit eruption, they were simultaneous at the time. The summit and the Rift Zone were simultaneously active. That the migration caused a very, very significant deflation of the magma system, and also some collapses and explosion events were happening at the summit, as summarized here, that began in mid-May 2018. And this caused a very sharp drop in the lava lake level in Halemaumau at the summit there. Here we see it on 6th of May, but a few days later, the lava lake was no longer visible at 320 meters. So the thing really, really subsided very, very, very quickly. Here's another video, which I hope works. And it shows that the rapid draining of a Halemaumau lava lake on the 7th of May. And there's some sound effects with this too. So as it's dropping, of course, the whole surface is unstable and it's all chaotic like it shows here, with spattering and low fountaining and so on. And those are the actual sounds captured at the time. Then I mentioned earlier that we had these collapse explosion events. So we had tremendous, as this was erupting down rift, the summit was collapsing. And so we see these huge collapse events, which actually produces very, very high plumes of debris. And this is one of them on May 27th. And there was a whole series of these, more than 60, well, there were 62 of them total. And all of them had very, very distinct patterns of changes in the tilt of the magmatic system, and also the earthquake activity. You see, there's very good correlation for each of those type of events that we saw.
Bob, what was the red line on that chart?
Okay, let me back up. That is the cumulative count for the earthquake activity. Okay. You can see how it drops off and it flattens out on top. Now, this slide shows the really big changes at the summit caldera. This is seen from the Hawaiian Volcano Observatory. The top slide shows what the caldera looked like. in April 14th. And after those series of collapses, you can see what it looks like now. The caldera is greatly enlarged from the collapses. And here's another view of that. The top part of that slide shows the activity before the collapses. And the lower part, you can see that the Halemaumau crater now is much bigger and deeper. I think that's pretty dramatic there. The blue line was the April profile of the caldera. Then after the explosion collapse events, the red line, August, and you can see the amount of collapse was up to 1,600 feet. So the really dramatic. Then after that series, there was no more live lava to be seen after September 5th, either at the summit or on the rift zone of Kilauea. So then the volcano, Kilauea, remained inactive until late December in 2020. So about a 2-year period of quiet. And that just shows it here very dramatically with the top part of it shows the volcano deformation changes, and then the big eruption in 2018, very sudden change in the shape of the volcano, then a 2-year pause in activity, and then eruptions began again in 2020. You see the big earthquake spike too that was related to that eruption. Then, interestingly enough, this is something totally no one expected. Fresh water, ponded water, appeared in July of 2019 during the period when there was no magmatic activity. And this shows it. It started off as a very small pool of ponded water. And this hadn't been seen in the historical time observations of Kilauea. It might have happened in the geologic past, but in historical records, there are no observations of fresh water at the bottom of the crater. And here are 2 views of it. The pond got larger and larger, and it rose in level. And it was a very steady growth in the depth of the water pond, and got up to more than 50 meters by December 2020. Keeping in mind the volcano is still quiet. This is just the water level rising inside the crater. And here's a webcam view of the ponded water in Halemaumau, just a few hours before the start of a new eruption.
Bob, where was the water coming?
Okay, I'm glad you asked that question. This is very interesting because it hadn't really been studied before, but the most widely accepted interpretation of that now, that was the recovery of the water table after the sudden collapses. The water table rose again because the depth of the collapse was deeper than the water table level. So it's just the water table rising to readjust. And then by the night of the 20th of December, there was a new eruption of magma now, and it boiled off all of the ponded water, so that disappeared after that. And now we're going to get to the part of kind of the post-2018 activity. This graph just sort of is a graphical summary of that. That started from the time after the 2018 eruption was over. There's no lava observed at all until 2020. And it again shows the volcano deformation, and you see the deflations with each eruption. The pink area, or kind of the tan area, shows magmatic activity again, or volcanic activity again. And that's also reflected in the earthquake data along with the ground deformation data. Oh, endogenous growth. In fact, I'll show a picture of that later. This was a time when it was, during a time when it was active. There were also periods of time when the whole lava lake would kind of just puff up and swell, but not break the surface. But you can see dramatic changes in the height of the lava lake, and it would change. So here's just a picture of the view of the lava lake activity in Halemaumau on 30th of September, 2021. Okay, we hope now this is going to be a video showing some of the activity in November of 2021 after the volcanic activity resumed. Come on, it should work. There we go. And so this is just one of the vents on the lava lake that was bubbling and gurgling and throwing up spatter. I think that gives you an idea of it. I'll go on to the next slide now. Okay, I mentioned endogenous growth. Here's a picture of Halemaumau lava lake during a period of activity, but not dramatic fountaining and everything. The main action was this internal growth of the pool of lava. As you'll see in the next. You see how that's puffed up? But you don't see much molten material being, the whole thing is just being bowed up, and that's up to 50 meters. It went up like this. It would just rise up and then come back down.
How much time is involved?
Okay, the time is involved here, March through November. And so at various stands, they had time-lapse images of this, and they made a video out of it.
So now, in its highest tier, was this above the old lake level pre-18?
No. Oh, okay. The question was, at the height of these endogenous growth, was it higher than the 2018 lava lake? And the answer is no. Here's lava lake activity within Halemaumau during January and March of this year's. So you can see this is pretty dramatic here. This is a nighttime view of a lava lake circulating around with localized popping up of magma, lava. But there were a few pauses during the times of these volcanic periods. And I'm kind of doing this chronologically now. So by April, there was a period of time when there's a pause in the lava lake activity. And when there's a pause, not much is happening. It's not rising, and it's not fountaining or spattering or circulating. Then we're going to get to the most recent activity at Kilauea in June of this year. And this is a video that captured the start of this particular episode. It was 4:43 in the morning. Very dramatic. You had fountain heights of up to 250 meters during this episode. Okay, now I'm going to have daylight view of this, what's going on, rather than the early morning view. These videos are actually, oh, that's the sound effects of the, what's going on with the helicopter noise. If you see the shadow of the helicopter on the floor there. And then here's a view of what the caldera looked like on June 20th. Because the eruption had paused on the 19th. And as I speak now, it is still paused. Now, that doesn't mean the eruption is over, but it's taking a pause for several months now. We'll see what happens next. You can see there's no circulation, there's no red stuff anywhere. It's just all cooled over other than some fuming areas. And this is kind of an interesting map. Here's a thermal map that measures the temperature of the surface. And the blue color indicates very, very relatively cold temperature. And it means solidified lava. This is crusted over, except for one little tiny area to the north there, a small ooze out of residual lava. And but basically that eruption is now ended or paused since June 19th. Now, having said that, keeping in mind there's another volcano on the island. Mauna Loa, while Kilauea was erupting, also began to erupt in 2022. This is very rare. Simultaneous eruptions of Kilauea and Mauna Loa are exceedingly rare. They've been very rare since 1927. Before that, it was more common. But for almost 100 years, there have been only 2 instances of simultaneous eruptions at Mauna Loa and Kilauea. One was in 1984, and the current one last year. That was November, December. And here's a picture of the vent fissure on the morning of the 28th, just a few days or a day later. And this is really pretty spectacular, I think. These are very fluid lavas. These are basaltic lavas that this braided pattern is very, very common as the lava flow goes downhill. And here's the main vent for that event at Mauna Loa, Fissure 13, on 29th of November. And here's some action on that vent, high fountaining.
What's the temperature of that? 3,000 degrees?
It would be about 1,100 degrees centigrade, more or less.
How close did this flow on Mauna Loa get to the meteorological station up there?
It closed the road and cut off the access to the Mauna Loa Observatory. And I'll show a map of that in a minute.
Did the berm that they had made protect it?
No, it cut the road. It did not affect the observatory, the access to it. Now, I think that's kind of a spectacular picture of the lava flow advancing toward the Saddle Road, which is the main highway that links the east side of the island of Hawaii to the west side. It is the best road if you want to get from one side to the other, rather than going all the way around the island. And in this slide, you guys should see in the background there the shield shape of the summit of Mauna Loa, because this eruption main centers on its northeast rift zone, not the caldera summit. And this is kind of an interesting shot of one of the flows on December 7. And pay particular attention to a blob that's kind of floating down the river here on the lava river, lava boat. So we're right in the center of the screen now. It's carried as a more solidified blob floating on the. Oh, and here, interestingly enough, you'll see in the background Mauna Kea volcano, because this is the saddle area between the two volcanoes.
What was the speed of the lava?
It here on the 7th, because it was starting to slow down, it was probably on the order of maybe 15 miles per hour or something of that order. Lava flows can, depending on the slope, can be as high speed as 50 miles per hour. That's been the highest observed rate of a lava flow in Hawaii. On very steep slope, very hot fluid lavas. I don't know this one exactly. I could find out, but I'm sure there's data on the flow rate of this. And by December 8th, things start to slow down a bit. The lava flow got more channelized rather than spreading out in these braided forms and stuff. It started from a more narrower flow of lava, as you see here. And I'll do the video here. That's again helicopter noise. That's not lava noise. And you can also see around that vent there, a spatter cone has formed. That little conical mound of material that's from the eruption. Okay, John, this is going to answer your question. Here's the Mauna Loa Observatory is indicated on this slide. And you'll see that the flow cut the access road to it, but it did not affect the observatory at all. But it did approach within 2 miles of the Saddle Road, which is the major highway connecting the two sides of the island.
What is the green line?
That is the. That's a good question. They don't give it here. Oh, no. Yes, they do. It's the national park boundary. Okay. Yeah, this is in the fine print up there in the index. Anyway, that eruption was pretty short. It only lasted for about 2 weeks, but it did have some potential for major hazards. Had the vent migrated farther to the northeast, the lava flows might have then started to affect suburban Hilo, the city of Hilo. But this was high enough up, and it stopped within a very short time, after about 2 weeks. And it didn't cut the highway, and it didn't cause any major damage, other than the fact they had to reopen the road to the NOAA Observatory. Now, as you folks know, the NOAA Observatory is the station where measurements of carbon dioxide are made on this whole climate change thing. It's a very, very precise measurement of the CO2 content of the atmosphere, which is, as you know, been rising with time. And so that's the observatory there that does that.
Obviously, on the road, crossroad, is that the access up to Mauna Kea that's going off to the north?
No, the question was, is that road shown there, the access to Mauna Kea? No, that is the black line is indeed the Saddle Road, which is a 4-lane road. The Mauna Kea access road is farther to the east. Okay, that kind of ends what I was going to show you about what has happened at the two volcanoes since 2018. So what's going on now? Well, there's no visible active lava either at Kilauea or Mauna Loa since June 19th of this year. I was hoping to bring something that was, it's happening now, but sorry, can't do that. However, the Kilauea volcano is showing very, very slight level of unrest, meaning by that the volcano is gradually swelling up and the earthquake count is picking up a little bit, but nothing out of the ordinary, is within the ranges that have been found before. But the style of deformation is similar to what happens before the outbreaks at the summit again. So how long will this pause last, or what would be the threshold if we get another breakout at Kilauea? We don't know. Mauna Loa is also undergoing very slight inflation. Both volcanoes are very, very closely monitored for earthquake activity and ground deformation. And at the moment, the HVO staff is not making any predictions on any imminent outbreak at either volcano. But be certain that there won't be any surprises, any major changes in either the seismicity or ground deformation rate will be noticed, and then that will give a better idea of a near-term forecast of the next outbreak. Oh, now, for those of people who have the opportunity to travel to Hawaii this past few months, if you're at the national park there on a clear night, you have some dramatic views of the lava lake activity, as shown here in a National Park Service photo. In fact, that's one of the real beneficial parts, having a national park there. The park was designed specifically to allow people to have access to active volcanoes, and here we have a great example of that. And that ends my chat, and I'd like to thank all of you for your attention, and also to all my HVO colleagues for their help and images and videos. In fact, I might mention that many of the videos that I showed are all available for looking at on the HVO website, which has a abundance of active scenes of volcanic eruptions. So just Google HVO Volcano Observatory, and you can get on their web link and video link, and you can see many of these videos that I've shown you here. So thank you very much. I appreciate your attention.
Both the national park and the volcano have.
The Volcano National Park is open now. They were closed there for a little while during some of the episodes, but they're open now. And I think, but I'm not sure, the Volcano House is also open. Yes.
When you talk about earthquakes with this volcano, are they rifts and vents from the lava or steam or something else?
Both, actually. Okay. The question was, are the earthquakes that are recorded in Hawaii related to lava or steam or something else? And the fact of the matter is that whenever you have solid rock fracturing, you create earthquakes. Either the pressure, the buildup of steam could fracture the rock, but the more common cause of volcanic earthquakes, call them that, is the rise, the molten magma trying to get its way up. And in order to get its way up, it's got to fracture the rock to rise some more. So that's why before an eruption, lava is coming up or magma is coming up, and then ultimately the threshold is broken and you have actual eruptions. Yes.
They do mass balance calculations to determine how much lava comes out, and then does that lead to is the amount of lava coming up from below more or less constant? Is there
Okay, The question was, are there any kind of mass balance calculations done between what is erupted and thrown out and what is changed in the shape of the volcano? Yes, there are. There are very specific examples of those. In fact, these eruption collapse events I talked about, I don't have the number in my head, but the amount of material thrown out in these explosive events is pretty much equal to the volume of the material of the collapse. So that was about equal. But that varies, and the rate of magma formation at the Hawaiian hotspot is pretty steady and constant, although in recent decades it has increased slightly over historical times.
We do have some Zoom questions. So, Bob, in 2018, why did magma move down to lower east rift zone after 35 years of stable eruptive behavior from the vent at Puuoo?
Yeah.
What triggered the change?
Okay, that's a good question, and the answer is not absolutely clear. One big factor was there was a magnitude 6.9 earthquake that occurred in May that affected the southward flank movement of the volcano toward the sea. So that might have weakened and actually expanded the rift zone to make the magmas to flow down rift more easily. So that magnitude 6.9 might have been a contributing factor.
Do you know where the epicenter was in that earthquake?
Was there on the Big Island. I don't know where exactly.
So down in land. Is it a big overhanging ledge that might collapse?
Okay, the question was, is the new land that formed a big overhanging ledge that could collapse again in the future? That's a great question. In the short term, when the lava first goes into the ocean, you have a very unstable pile of rubble, basically, and it is very, very hazardous. And you get so-called bench collapses because it's not well supported. But if it goes on long enough, the newer lava coats over the earlier materials so that it's like building a delta in a river system. If it goes on long enough, it actually stabilizes a bit. And that new land now is pretty stable unless you get to the edge of it. In fact, during the eruption earlier on, during 2018, there were some dramatic lava delta building episodes, and it showed that they do collapse periodically.
Question again from Zoom. Is there any place in Greater Yellowstone where one could observe in the geologic record a similar lava lake and eruptions and collapse as we see in this presentation?
Wow. Well, okay. First of all, the difference between a Yellowstone volcano and a Hawaiian volcano is the viscosity of the lava. And in Yellowstone, the typical eruption forms calderas. They're typically explosive eruption rather than these fluid lavas flowing gently for great distances down slope. So that you don't have shield volcanoes like we have in Hawaii in the Yellowstone region. You do get some basaltic lava flows, but they don't form the same landforms in general. And so that it varies depending on what is actually erupted. And in the Yellowstone region, the composition of the lava that is erupted is mostly rhyolitic, much more viscous and silica rich than the Hawaiian lavas. So you tend to get explosive eruptions and formation of caldera collapses.
Bob?
Yeah, John.
Same line, could you comment a little bit about what's going on in Iceland and the nature of the lava versus Yellowstone and Hawaii?
Okay, John's question was, what is the nature of the Icelandic eruptions compared to Yellowstone, and Hawaii. Well, first of all, Iceland is in a different context. Iceland volcanism is occurring because of the two plates splitting apart. So you have a divergent plate boundary that's allowing the magma to come up. And the composition of the Icelandic ones are basaltic also. So you get landforms and eruptive styles very similar to Hawaiian ones, but they tend to be more fissure eruptions. So you get sort of very flat lying rather than volcanic features in general. It sort of would be like the Columbia River Plateau basalts in that situation. Now, having said that, as you know, that Iceland has had some explosive eruptions that have disrupted air traffic in recent years because they had to shut down the airports in various parts of Europe because of the ash in the clouds.
All right, we have another question here. Let's see if I can state this. Maps of the west coast of the United States show the Pacific Plate moving northward toward the Aleutian Trench. Please talk about why the Hawaii chain is a westward feature instead of northward.
That gets very complicated because we have that plate called the Juan de Fuca plate, which gets in the way of the two. Some of you in the audience might have seen in one of the slides that the Hawaiian hotspot trail takes a bend. And that bend occurs at about 42 million years ago. So the generally accepted interpretation of that is that the motion of the Pacific Plate changed from what it is now, from what it was 42 million years ago. So my answer may perhaps relate to that question.
One more Zoom question. Are there any theories about what started this recent volcanic activity for the last few years?
Oh, well, it's sort of the same question we would ask about any Hawaiian eruption. It is a hot spot. It's a mantle thermal plume that rises from deep in the earth and actually ultimately rises high enough to cause partial melting of the solid materials. And that's going on all the time. And then you might have some local tectonic effect that might actually enable or favor the breakout of this material with time.
I think there's a related question too, which is, are these the two active volcanoes that you mentioned in the talk? Are they somehow related underground? Are they plumbed together?
Okay, that's a great question. The two volcanoes share the hotspot, the Hawaiian hotspot, so that the thermal energy is the same for both of them. That just means that the hotspot is probably 100 miles or more in diameter or even greater. So it feeds both volcanoes. In fact, it's also feeding the new volcano, Loihi, which is erupting offshore of the Big Island. So the hotspot is big enough to feed all three of those. Now, from what data we have from historical eruptions of both volcanoes, that over time, either Mauna Loa tends to be active for decades at a time, with Kilauea being relatively quiet, or Kilauea being very active and Mauna Loa being very, very quiet. So as the hotspot thermal plume comes up, it actually then branches off in some way that there are two different magma reservoirs. There are two separate magma reservoirs. And it's just a question of what is the mode of filling of one or the other. And that we don't know. Why it all of a sudden would go to Kilauea more than it does to Mauna Loa.
So
John.
on your discussion of the size of the magma plume, if you went down, say, 100 miles and looked at the chimney, any idea about how big that is? Is that fairly small?
Well, actually, it can't be too small. I mean, first of all, I should back up a bit. You know, the concept of a magma reservoir is not what we think it is. It is not pure liquid. What it is a mass of rock that is infiltrated by little seams and blebs of magma, so that the density is different. So there have been a lot of seismic studies done of what's beneath Yellowstone as well as Kilauea. And there are computer models of what these might be like, and these are on the scale of tens of miles to over 100 miles wide across the, let's say, the thermal plume area coming up. But the reservoir at Kilauea is actually, if you seismically configured, is relatively small. It's it's right beneath the summit area, and it doesn't extend very far away from the boundaries. Yes.
Being like 100 miles big. Would Mauna Kea be ever erupted again, or even Haleakala?
Okay, that's a good question. The question was, could Mauna Kea ever erupt again, or even Haleakala on the island of Maui? There was an eruption. Okay, keep in mind that the island chain gets progressively older as you go up the chain, because the plate is moving away from the hot spot that causes volcanism. So Haleakala, there was an eruption back in the 16th century, one little historic eruption in Haleakala, and Mauna Kea itself has not erupted since 4,000 years ago. And it's so, if the plate tectonics theory is right, and the hotspot theory is right, we should not expect something at Mauna Kea or Maui again. But we could be wrong. Well, thank you very much for all your attention. Good question. Appreciate that.
So, thank you, everyone. We'll be here for a few minutes if there's some questions that you didn't want, that you would like to ask, but didn't want to ask out loud. If we could get help with the chairs on this side go that way, the other chairs go that way. October 3rd, Dr. John Bird is going to talk about the Tetons, which will be a absolutely fascinating talk, and he'll bring some new work to our auditorium here. So again, thank you for coming, and hope to see you all then. We have a small present for Bob.
Oh, thank you very much.
And work putting this together.
I appreciate it. I will look at it when I leave.
Yes, well,
Thank you.
before.
Oh, even before. Well,
Yeah.
okay.
So again, please join me in thanking Dr. I.Tilling for an incredible talk, and
Thank you.
and I love those videos. Wow.
Oh, wow. Thank you. Very nice. Nice rock sample.
It's a mammoth tooth. It's not just a rock.
Is
It's
it?
a piece of a mammoth.
Oh, I didn't know that.
Yeah,
Well, thank you.
yeah, this is
Mammoth tooth. Okay.
the whole card that explains
Okay.
everything.
Terrific.
Not just any rock.
Can I ask you a quick question?
Yes.
Which maybe I didn't understand, but why aren't we seeing more